Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. In this December 2025 lecture series, we are discussing about data reduction techniques in time frequency and multivariate analysis in biomedical signal processing. Our first thing is why data reduction matters in biosignal processing. We know that biosignals like EEG, EMG and ECG, they generate massive complex data streams which is difficult to maintain, which is difficult to store because the recordings they produce terabytes of information which must be stored, transmitted and analyzed efficiently for precise outcomes and results in clinical validation. Here, the critical challenge include storage limitations, bandwidth constraints, and noise contamination, and significant data redundancy that obscures meaningful patterns. Here, we need efficient data reduction techniques to overcome the critical diagnostic information and which enables a real-time analysis, making the difference between the our tested data as well as our original real-time signal information. See here, our real pain point is EMG. It interfaces a struggle with motion artifacts and noise interference, which creates frustration during movement-based assessments and reducing diagnostic confidence for clinicians. Here, our first thing is clinicians they need a clear actionable data for rapid diagnosis without wading through noise and artifacts. See here the patients they depend on comfortable reliable monitoring that don't sacrifice accuracy for convenience. See here I've included one case study, which focus on core problem statement. Here, how can we reduce biosignal data size 70 to 90% without losing diagnostic value or introducing artifacts that compromise clinical decisions? Our key requirements, which includes minimal loss of clinically relevant features, effective noise and artifact reduction, computational efficiency of real-time processing and scalability across different biosignal types. Here, our case study, which mainly focus on electrochemical impedance spectroscopy data reduction for neural interfaces, where massive data sets from electrode arrays must be compressed while preserving tissue interface characteristics critical for long-term implant performance. So we need a proper data reduction techniques for efficient data handling. See, here we have diversified approaches. Here I've included ideate and design thinking stage. Here I've mentioned ideate here. And in this part, advanced filtering techniques, intelligent segmentation, wave transform analysis, which plays a major role. See, in advanced filtering techniques, we can use adaptive filters, bandpass optimization, and multi-stage filtering cascades to isolate signal from noise. And with the help of intelligent segmentation, the event-driven recording that captures only meaningful signal epochs, reducing storage by 60 to 80%. And wave transform analysis, here we use time frequency decomposition. It's perfect for non-stationary EMG signals with localized feature extraction. Here, our consideration, which includes data volume, real-time constraints, interoperability of for interpretability of clinicians, and the outcome is which connects signal processing with healthcare innovation. The activators design think real-world applications. Here I have given a scenario like a healthcare analytics company process continuous EEG data from ICU patients to detect seizures in real time. Here we can incorporate hybrid ML approaches also, combining traditional compression with a deep learning for context-aware data reduction. Our outcome, it should be to connect signal processing with healthcare innovation. That's it. See, here in data reduction techniques, we have algorithm development, a front-end circuit design, dimensionality reduction, and simulation and modeling. With the help of proper multivariate component analysis and machine learning algorithms, we can easily enhance the precision and accuracy of clinical data validation part. See here, in validation methodology, we have a dataset diversity, performance metrics, and user feedback loops. Here, see the diagram. Before reduction, after reduction, here it results demonstrates significant improvements across all key metrics, validating the integrated design approach. Next, key data reduction techniques in biosignal processing, which includes signal segmentation, feature extraction, dimensionality reduction, wavelet based filtering, and front-end hardware optimization. See here, in this part, we have signal segmentation, feature extraction, dimensionality reduction, wavelet based filtering, front-end hardware optimization. And this is our summary part. Here we have to empathize a real pain point in data reduction, and we'll focus case study for defining the problem. And ideal part, we're exploring diverse approaches to biosignal data reduction, and finally we can use a perfect data reduction techniques to enhance the clarity and clinical validation of our medical data. And here I've included assessment and references. Our assessment task is case study and presentation, which I have taken from Philips Healthcare, and here I've included some reference links. Thank you for watching.